All right, welcome. So, to follow up our series on Macaulay's method of beam deflection, let's say we are given this problem and we are asked, using Macaulay's method, determine deflection at B and the maximum deflection of the beam shown. Okay, so we are given Young's modulus as 200 giganewtons per meter square and moment of inertia as simply this. So we'll have the beam here. Let's outline the free body diagram of the beam, which is the very first thing to do, FBD. So bring down the beam at point A, which is that we have a pin, and for a pin support, we have two reactions, one vertical, so this is simply RAX, RAY, and one horizontal, which is simply RAX, all at point A. At point B, we have a 10 kilonewtons force acting downwards there. So we simply have a 10 kilonewtons force at point B, 10 kilonewtons force, this is point B. Now between C and D, we have a UDL whose value is 20 kilonewtons per meter. And I said to convert a UDL to point load, simply multiply the UDL to the length covered. The length of this UDL here is 2 meters. So we simply have 20 times 2. It becomes a point load. And I said this point load should be placed at the middle of the length of the UDL. If the length of the UDL is 2 meters, middle of 2 simply means 2 divided by 2, which is actually 1. Okay, so from C to D, we have a UDL, which we've converted now to point load. So it acts at the middle. The value of this point load is simply 40 kilonewtons. Okay, so it's actually 1 meters apart. We'll have here 1, okay, and then 1 meters as well. Okay, so between C and D, all right, so that becomes the point load of the UDL. Finally, at point E, we have a roller whose and for a roller, I said we only have one reaction, which is normal to the surface. So at point E, we have a roller, simply just a reaction, simply call this RA y normal to the surface. This is point E. This is 2 meters, this is 2 meters, and this is 1 meters. Alright, so that gives us the free body diagram of the system. So the first thing to do, of course, is to obtain the values of these reactions or known reactions. So simply, we employ our equilibrium law. Recall the first equilibrium law, summation of horizontal forces, summation f of x equals 0. Alright, so we equate all the horizontal force on the system, sum them up and equate them to 0. And if we look at this diagram now, it's only one force that we have pointing in the horizontal direction. That's simply RAX. So from the law, this actually implies that the reaction at point AX is actually equal to 0. So that one is off. The next equilibrium law simply says summation of vertical forces, summation f of y equals 0. So we simply consider vertically upward forces as positive and downward forces as negative. Okay, so this law simply means look at the beam, sum all the vertical forces on the beam and equate them to 0. So let's start from the beginning now. At point A, we have RAY pointing upwards. So from the law, vertically upward force are positive. So we simply have RAY positive because it's pointing upwards. At point B, we have a 10 kilonewtons force acting downwards. So that force is negative because from the law, downward forces should be considered as negative. So we simply have minus 10. Next, between C and D, we have a 40 kilonewtons force also pointing downwards. So it's also negative. So we have minus 40. And finally, at point E, we have REY pointing upward. So it's positive. We simply have plus REY. The whole of this is equal to 0 from the law. Okay. So this simply gives us RAY. Now minus 10 minus 40 gives us minus 50 plus REY, and that's equal to 0. So we can simply send minus 50 over to this side of the equation. If we do that, we are simply going to obtain RAY plus REY is now equal to negative sign crosses an equal to sign becomes positive. So we simply have 50. Let's call this equation 1. Of course, equation 1 is actually what? A single equation having two unknowns, which makes it very impossible for us to solve. So, like I always say, at this point, you simply what? Take moment about any point of the unknown to obtain the unknown reactions at least one. And I said the best place to take moment is consider the beam where you have numerous of unknown. Take moment at that point. We have about two unknowns at point A, RAX and RAY. So it is wise enough for us to take moment about point A. All right, so let's do that now and see. All right, so we simply take moment of forces at point A. So take moment at A. And not forgetting our law, summation of moment, okay, at A is equal to 0. We consider clockwise moment to be positive, anti-clockwise moment to be negative. All right. So taking moment at A, the moment of these two forces RAY and RAX about point A automatically becomes 0. So that's off. We now have to take moment of this force, which is the 10 kilonewtons force at point B about point A. Now this force is pointing downwards, and therefore the moment of this force will turn about in this direction to point A, simply or turning in this direction, which is actually um, from our direction is actually clockwise, so it's positive. It turns about in this direction to take moment at point A, so it's positive. And distance it takes this force to get to point A is simply 2 meters. Therefore, the moment of that force simply becomes 10 times 2. Okay. Next is the 40 kilonewtons force. This force is also acting downwards. This force will also turn about in this direction. Okay, also in this direction to point A, and that direction is also clockwise. Distance it takes this force to get to point A is simply 1 plus 1 plus 2, which is a total of 4 meters. So we simply have that moment to be, and it's positive, not forgetting, plus 40 times 4. All right, so we have that. Finally, we take the moment of this force REY about point A. This force is pointing upwards, so which means this force will turn about this direction. It turns in this direction to take moment at point A. Therefore, that direction is simply anti-clockwise. Okay, finally, the moment of this force, okay, turns about in this direction to point A, and total distance it takes this force to get to point A becomes total length of the beam, which is actually 2 plus 2, 2 plus 1 plus 1, which is 4, 5, and 7 meters. So we simply have minus RE y times 7. 7 becomes minus because the moment of this force is anti-clockwise to our direction. From here, it's anti-clockwise, so it becomes negative. All right, so we'll have that. Okay, so let's evaluate this now and see. 10 multiplies 2 will simply give us 20. Okay, plus 40 multiplied by 4 will simply give us 160. Okay, minus 7 REY, and this is actually equal to 0. Of course, 20 plus 160 will simply give us 180 minus 7 REY equals 0. Okay, so let's simply send minus 7 REY over to this side of the equation. Negative sign crosses an equal to sign becomes positive. So we simply have 180 equals 7 REY. Okay. Alright, so to make REY subject, which is the unknown reaction at point E, simply divide both sides by what? 7. This actually implies that REY is now 180 all over 7. And therefore, the reaction at point E is now equal to 180 divided by 7. Okay, so that simply gives us 25.7 kilonewtons. All right, so this becomes the unknown reaction at point E. All right, so we can now simply substitute this equation into equation 1 to obtain RAY. Okay, so let's do that now and see. So from equation 1, we have RAY plus REY equals 50. So we already know the value of REY now. REY gave us 25.7. So this simply means RAY plus, in place of REY here, we'll simply replace it with 25.7. So plus 25.7, and that's equal to 50. That simply means now to make RAY subject, simply send plus 25.7 over to this side of the equation. Positive sign crosses an equal to sign becomes negative. So we have RAY equals 50 minus 25.7, and therefore RAY is now equal to 24.3 kilonewtons. Okay. All right. So having known these reactions now, next thing to do is simply what, plug back these reactions into the beam, and then you can start your what, deflection analysis. Let's do that now and see. All right. So we simply plug back those reactions into the original beam, not forgetting, plug back those reactions into the original beam. Okay. So this becomes the original beam that we have. RA will obtain the value. Okay. RAY simply give us 24.3 kilonewtons, and then we also obtain REY. That simply gave us 25.7 kilonewtons. So you plug back those reactions into the original beam. This distance is 2 meters, this is 1 meters, this is 2 meters, and this is 1 meters. All right, so according to Macaulay, using Macaulay's method to carry out this beam deflection analysis, now we are supposed to section in such a way that um, the very last load, all the loads on the beam must be included on the section, and the last load before the last point of the section must be what involved. The last load before the last point on the beam must be involved in the section, and the very last load is simply at the UDL, which ends at point D. So notice that if we take this section here along DE now, along DE, if we take this section, it will be difficult for us to find an accurate length for what, the UDL. This UDL is now placed in between from C to D. It will be difficult for us to find an accurate length for the UDL, and as such, integrating this length will be a very big issue for us. So according to Macaulay's theorem, if I have my UDL to occur in this manner, what I will do is this: simply extend the UDL. Simply extend this UDL to get to the end of the beam, and then you counterbalance it under. Okay, simply extend the UDL and then you counterbalance it under. With this now, it becomes easier. You can now take your section. You now know that you have what, this is still in equilibrium, because remember, upward force here is positive, downward force here is negative. So the two of them have the same value. So the beam is now what, in equilibrium. Okay, so you can now take your section. All right, so taking your section here, x. Okay, distance from point A to the point of section according to Macaulay is simply what, x. So we'll simply have there to be x. So if you have been following my series on Macaulay's method of beam deflection, I said after obtaining this point of section, next thing to do now is to obtain the distances of each of the loads about the point of section. We have established that from point A to the point of section is x meters. What is now the distance of this load at point B to the point of section? We need to obtain this distance, okay, to the point of section. And of course, I've said in my previous videos, it is not a big deal. Since I am now at point B, it means I no longer need the distance behind. I'm no longer moving from point A, I am moving from point B. So which means this 2 meters behind, simply take it away from x. That gives you distance from point B to the point of section. So you simply have here x minus 2. So this gives you the distance of this beam, of this load at point B down to the point of section. Okay. All right. Next is to find the distance of this UDL from point C to the point of section. Okay, distance of the UDL from point C to the point of section is still the same thing. It doesn't change. Since I am now at point C, it means I have to now what, remove every other distances behind from X. That gives me distance from point C to the point of section. And the distances behind include 1 plus 2, which is 3 meters. So simply take away 3 off from X. Okay, so I will simply have X minus 3 x minus 3. This is now the distance of this UDL from point C to the point of section. And finally, I have from point D as well to the point of section. So I need to find this distance, the distance of this other UDL from point C to the point of section. I also need to obtain this other distance from point D to the point of section, being the distance of this UDL at point D. Okay, so that distance is also, since I'm at point D, it means I'm no longer in need of every other distances behind. Behind, I have 2 plus 1 plus 2, which is about 5 meters. So simply take away 5 off from x. That gives you distance from point D, which is the distance of the UDL about the point of section from point D. So I'll simply have x minus 5. Okay, so the length of that UDL about the point of section from point D is simply x minus 5. So after obtaining these distances, now you can now take moments about the section. So we simply call that mxx, moment about the section xx. And according to Macaulay's theorem, upward forces must always have positive moments. Meanwhile, downward forces should have negative moments. Okay, so if we do that now, I have 24.3 kilonewtons at point A. Distance of this force to the point of section is x meters. And I know that moment is actually force times distance. Okay, so if the force is 24.3 and the distance is x, it means the moment of this force becomes 24.3 times x. Okay, that becomes the moment of this force about the point of section. Now, after the very first moment, Macaulay says, introduce a Macaulay bracket. So I simply bring down a bar. This bar is actually what a Macaulay bracket is, a bar to separate each of the moment from themselves. So I will introduce what? The bracket after the first moment. Now, this force is pointing downwards, so it's going to have a negative moment according to Macaulay's theorem. And the distance it takes this force to get to the point of section, not forgetting, remains x minus 2. So the moment of this force about the point of section is simply what? Minus 10 into x minus 2. So I'll simply have this. After this moment as well, introduce the Macaulay's bracket again. So I still bring down a bar because I still have another what? Load. That's the UDL now at between point C to the point of section. So because of this UDL, I will introduce what? A Macaulay bracket. So I need to take moment of that UDL about the point of section. Okay, so first thing first, remember this UDL now has a length of what? X minus 3. That becomes the length of the UDL about the point of section from point C. And to convert a UDL to point load, not forgetting, you multiply the intensity of the UDL to what? The length covered. So, okay, so let's say this is the beam and the length covered by this point C, and this is the point of section XX, and we've established that the length covered by this UDL and we've established that the length covered by this UDL is simply x minus 3. And I said to convert a UDL to point load, first of all, you multiply the intensity of the UDL to the length covered. The length now is x minus 3. Therefore, the point load becomes 10, which is the value of the UDL times x minus 3. This gives us what? The point load. This is a point load and not a moment. So 10 into x minus 3 is actually what? A point load. And we said afterward getting this point load, place this point load at the middle of the length covered by the UDL. So if here is point C and here is the point of section, this is distance of this UDL x minus 3 about the point of section. I've converted this UDL to point load. I have 10 into x minus 3. Now I have to place it at the middle of the length, which is simply 10. This is the load, 10 into x minus 3. That's the load. Middle of this length now simply means from point C down to this load is simply x minus 3 all over 2. Same thing happens here. From this load to the point of section is simply x minus 3 all over 2. Okay, so this gives me what? The middle of the length. Okay, middle of the length x minus 3. So the moment of this load 10 into x minus 3 about the point of section becomes 10 into x minus 3 times total distance it takes for to get to the point of section, and that distance remains what? X minus 3 all over 2. Alright, so the moment of this force is now equal. First of all, it is acting downward, so it's negative. So I simply have minus 10. Converting this first to a point load, simply multiply by x minus 3. This is the load. And distance it takes this force to get to the point of section is simply x minus 3 all over 2. So I simply have times x minus 3 all over 2. Okay, that gives me the moment of that load from point C to the point of section. Next up, I have again a UDL from point D to the point of section, and this UDL now is acting where upwards. This UDL is facing upward, so which means the moment of that UDL is going to be positive. Again, distance it takes this particular UDL from point D to the point of section remain x minus 5. That distance is given as x minus 5. So just like in this case now, I have to first of all convert this UDL to a point load. So I will still bring down another Macaulay bracket for the last moment of the last UDL. Since this force is pointing upwards, it's going to give us a positive value. So simply plus, the intensity of the UDL does not change, it still remains the same, 10 kilonewtons per meter. So I'll simply have plus 10. Now, converting this to point load, I have to multiply this 10 to here, the length covered. The length covered is simply x minus 5. This is the length covered by this UDL now from point D to the point of section remain x minus 5. But this is actually what a point load and not a moment. To convert this to moment, it means just like I explained here, I have to place it at the middle and multiply by what the middle of the length, which is like here and I had x minus 5. Okay, let's say all right, so 10 into x minus 5 gives us the point load, and of course if I place it at the middle is simply x minus 5 all over 2. That becomes the middle. Same thing here, x minus 5 all over 2. So this is the point of section now, xx. I want to now take moment of this force about the point of section. The force itself is 10 into x minus 5. Distance it takes this force to get to the point of section is x minus 5 all over 2. So which means I'm simply going to multiply this whole value 10 into x minus 5 by x minus 5 all over 2 to give me what? The moment. Alright, so I'll simply have here times x minus 5 all over 2. So this gives me what? The moment of the whole force about the point of section. Alright, so I can rearrange this equation. If I do that, I will simply have moment about section xx is now equal to, this remains 24.3x, 24.3x, okay. Put down your Macaulay's brackets. Here now, I have minus 10 into x minus 2. Okay, put down your Macaulay's brackets. I have here minus 10 into x. So please take note, this becomes minus 10 divided by 2. Oh, okay, minus 10 divided by 2 into, I have here x minus 3 times x minus 3. That will give me x minus 3 all squared. And then my final Macaulay's bracket, same thing here. I have plus 10. Okay, 10 divided by 2, it becomes 10 all over 2 into, I have here x minus 5 times x minus 5 simply gives me x minus 5 all squared. So this becomes my moment equation. I think I can still break this further because 10 can divide 2 here, 10 can also divide 2 here. So we can see further break this equation. Let's do that and see what we are going to obtain. Okay, all right, so I'll simply have moment about the section is now equal to, so I have here 24.3x, 24.3x. Put down your Macaulay's bracket. I have here minus 10 into x minus 2, minus 10 into x minus 2. Put down your Macaulay's bracket. Of course here, minus 10 divided by 2 will simply give me 5. So I have minus 5 into x minus 3 all squared. Okay, and then finally same thing happens here. Okay, um minus 10 plus 10 divided by 2 gives me plus 5, so I simply have plus 5 into x minus 5 all squared. So I simply have this becomes my moment equation now. All right, so after generating this moment, now recall from bending equation we have that ei, the squared y all over the x squared is actually equal to moment about the section xx. Okay, this is now the bending equation. So it means the whole of this is equal to what? Moment. And moment is given as simply what? This. So that simply implies that EI, the squared y all over the x squared, is now equal to, in place of mxs, we simply put in the whole of this variable. So we are simply going to have 24.3x. Okay, put down your Macaulay's bracket, minus 10 into x minus 2. Okay, put down your Macaulay's bracket. We have here minus 5 into x minus 3 all squared. Okay, and finally plus 5 into x minus 5 all squared. So I have this. So this gives me what? The flexural rigidity multiplied by double derivative of deflection with respect to x. Okay. Now, if I integrate this function with respect to x, I will obtain the slope equation. Okay, so integrating we have, okay, ei, this becomes the y dx. Of course, if I integrate the square y over the x square, remember integration is a direct opposite of differentiation. So if I integrate this function, I will actually what? Reduce it down to what? The first order derivative. So it becomes the y dx. And this now equal to, I will simply have 24.3. Now if I integrate x here, I will simply have x squared all over 2. Now, after the whole integration, we are supposed to introduce a constant of integration. Okay, after the whole integration, we are naturally supposed to introduce a constant of integration. And this constant, because this is not a definite integral, if it's a definite integral, we should have limits. But since this is not a definite integral, it means we need to introduce a constant. But according to Macaulay's theorem, it says this constant of integration should not be taken outside of where the Macaulay's should not be taken after the Macaulay's bracket. It says that the constant should be placed outside of the Macaulay bracket. So it has to be before the Macaulay's bracket, not after the Macaulay's bracket. Alright, so we simply say plus C1. C1 means the first constant of integration. So we simply have that plus C1. Alright, so after that, we can now integrate what? The function in this here bracket. So put down your minus 10. We have this. Now integrating x minus 2, according to Macaulay's theorem, you integrate it as a single variable function. The same way you integrated x here to be x squared all over 2. Okay, the same way we integrated x and we had x squared over 2. That's how you treat this function x minus 2 according to Macaulay's theorem. You treat it as a single variable function. So if you integrate, you simply have x minus 2 to the power of 2 all over 2, just like you're integrating a single variable function. So you treat it as that. Okay, so let's put down your Macaulay's bracket for this other integral. We simply have minus 5. Still the same theory. To integrate x minus 3 all squared, you have to integrate it as if you're considering a single variable function. So x minus 3 to the power of 2, if I integrate this function, I will simply have x minus 3 all cubed divided by 3. So that will simply give me x minus 3 to the power of 3 all over 3. If I integrate x minus 3 all squared. Okay, so I will simply have this. Okay, finally, integrating plus 5 here, this is plus 5 into, if I integrate x minus 5 squared, I will still also consider it as a single variable function. And if I do that, it will simply give me x minus 5. Since it's squared here, I will add 1 to the power. It becomes 3 to the power of 3 all over 3. Okay, so that gives me the integration of that variable. Okay, so let's try and evaluate and see. Of course, I have here 5 can divide 3. I also have here 5 can divide 3. I have here 10 can divide 2. So let's do all that and see. Alright, so if I rearrange this equation now, I will simply have ei dy all over the x is now equal to, so I'll simply have here 24.3 divided by 2 24.3 divides by 2. I'll put down my x squared plus my first constant of integration plus C1. Put down your Macaulay's bracket. I have here minus 10 divided by 2, and that should give me minus 5 into x minus 2 to the power of 2. Okay, I put down my Macaulay's bracket. I have here minus 5 divided by 3. Simply have minus 5 all over 3 into x minus 3 to the power of 3. Put down your Macaulay's bracket. Finally, here I have plus 5 over 3 plus 5 all over 3 into x minus 5 to the power of 3. Okay, so I will have here EI dy all over the x is now equal to, so I will first of all obtain 24.3 divided by 2. Let's do that and see. That gives us 12.15 x cube, okay, plus C1. Put down your Macaulay's bracket. This is minus 5 into x minus 2 all squared, okay. Put down your Macaulay's bracket. 5 here divides by 3. Okay, so minus 5 divided by 3 gives us minus 1.7 1.7 into x minus 3 to the power of 3. Put down your Macaulay's brackets. Same thing here, plus 5 divided by 3 gives us plus 1.7 into x minus 5 to the power of 3. So this is the slope equation. Okay, the equation with dy dx is actually what the slope equation. So this is actually the slope equation. So we integrate this equation further. We integrate this equation further to obtain the deflection equation. So integrating again, we have all right. So if we integrate this equation again, we simply have EI. If I integrate dy dx, I will automatically have y, which is actually the slope, which is actually the deflection equation, and that's now equal to. So I have here 12.15. If I integrate x squared, I will simply have x cubed all over 3 plus, if I integrate C1 is a constant, and I've always said integrating a constant simply was attach the variable of the integral to it. Since I'm integrating with respect to x and I'm integrating a constant, I will simply attach s to it. It becomes plus C1x. Okay. Now, of course, according to Macaulay, you don't add constants inside of the Macaulay's bracket. It has to be added outside the Macaulay's bracket. So, which means I also need to introduce the second constant of integration, and that's because I've taken another integration. So I need to add another constant to it. That constant is simply called C2, simply plus C2, which is the second constant of integration. So it should also would be outside the Macaulay's bracket. So I'll put down my Macaulay's bracket. Here I have minus 5, and now I want to integrate x minus 2 all squared. And according to Macaulay's theorem, if you're integrating this function, you integrate it as a single variable function. So the same way we integrated x squared here and we had x cubed all over 3, that's the same way we're going to integrate x minus 2 all squared. And if we do that, we are simply going to have x minus 2, okay, becomes to the power of 3 all over 3. So I will simply have this, okay. So I put down this Macaulay's bracket. Here I have minus 1.7. Okay, so if I integrate x minus 3 to the power of 3, I will simply have x minus 3 to the power of 4 all over 4. Okay, I put down my Macaulay's bracket here. I will bring down plus 1.7. Okay, 1.7. If I integrate x minus 5 cube, I will still have x minus 5 to the power of 4 all over 4. So I'll simply have this. Okay, so we can now evaluate. Of course, 12.5 can divide 3, and of course 5 can divide 3. Let's evaluate 1.7 into 4, 1.7 into 4 to see what we are going to obtain. Okay, so let's bring back the previous equation we have over here. So we simply have EIY, which is the slope, which is deflection equation, and that's equal to, so we have now 12.15 x cubed over 3, 12.15 all over 3 x cubed, okay, plus C1x plus C2, we have plus C1x plus C2 minus 5, okay, put down your Macaulay brackets, minus 5 all over 3 into x minus 2 to the power of 3. Macaulay's brackets are minus 1.7 all over 4 into x minus 3 to the power of 4. Put down your Macaulay's brackets plus 1.7 all over 4 into x minus 5 to the power of 4. Okay, that's the previous equation we had. All right, so let's now evaluate this and see. We simply have EIY, and that's equal to 12.5, 12.15. All right, so just to continue from where we stopped in the last, okay, from the last equation. So we have this. Okay, so let's evaluate this equation now and see. We simply have EIY equals here 12.15 divided by 3. We have 4.05. So this is simply 4.05 x cubed, okay, plus C1x plus C2. Put down your Macaulay's bracket. We have here minus 5 divided by 3. That's minus 1.7 into, we have x minus 2 to the power of 3. Okay, put down your Macaulay's bracket. Okay, we have here minus 1.7 divided by 4. That gives us minus 0.425 minus 0.425 into, we have x minus 3 to the power of 4. Okay, put down your Macaulay's bracket. Same thing here, plus 1.7 divided by 4. That's plus 0.425 into, okay, we have x minus 5 to the power of 4. Okay, so we have this equation. So all we need to do now is to find the values of the constants C1 and C2. And I said to find these constants, all we do is simply what? By applying boundary conditions. So I said applying boundary conditions, you apply two boundary conditions. The first boundary condition is at the very beginning of the beam. Okay, so we consider the properties of deflection and the values of the distance x at the beginning of the beam. Okay, and then the next boundary condition is at the end of the beam, which is at point E. These two boundary conditions gives us what? The values of the constant C1 and C2. So let's apply them now and see. Applying boundary conditions. Okay, BC simply means boundary conditions. Okay, so at the beginning of the beam, which is at point A, at A, okay, we have the values of x always is 0, and also there is no deflection at that point, so y is also 0. Okay, at point A, the x values is 0, and deflection at this point is not possible, so that point is also 0. So we substitute these conditions now into the deflection equation. So we have EIY, that's simply EI. In place of y is 0. So you simply put in the value as 0. And this is now equal to, we have here 4.05 x cubed. So in place of x, we put in the value as 0. That's simply 4.05. In place of x, we simply have 0 all cubed plus. We also have here C1x. So in place of x, put in the value as 0.
That becomes plus C1 into 0 plus C2. Pull down your Macaulay's bracket. Okay, here we have minus 1.7 into x minus 2. So in place of x here, we put in the value as 0. Now, so we have minus 1.7 into 0 minus 2 to the power of 3. Okay, pull down your Macaulay's brackets. We have here minus 0.425 into x minus 5 to the power of 4. So in place of x here, I'm putting the value as 0. That gives us minus 0.425, okay, into in place of x that we have 0 minus 3 to the power of 4. Put down your Macaulay's bracket. Same thing here. We have minus 0. Okay, sorry, we have plus here is positive, plus 0.425 into x minus 5 to the power of 4. So in place of this x, we also put in the value as 0. That simply gives us plus 0.425. Okay, into in place of x, we simply have 0 minus 5 to the power of 4. Okay. All right, so from here, e at multiply 0, everything here becomes 0. That simply gives us 0 is equal to, same thing here, 4.05 multiplied 0 is 0. So we'll put down 0 plus, same thing here, C1 times 0 gives us 0. Okay, plus C2, put down your Macaulay's bracket. Okay, we'll have here minus 1.7 into, so we simply have here 0 minus 2 remains minus 2 to the power of 3. Put down your Macaulay's bracket. Here gives us minus 0.425, okay, into 0 minus 3 here simply remains minus 3, okay, to the power of 4, into, put down your Macaulay's bracket. We'll have here plus 0.425 plus 0.425, okay, into 0 minus 5 here simply gives us minus 5 to the power of 4. Okay, to the power of 4. So we simply have this equation. All right, so here we have 0 equals 0 plus 0 here is 0 plus C2. Put down the value of C2. Okay, 0 plus C2. Now, I said that according to Macaulay's theorem, every value in the Macaulay's bracket which is less than 1 is completely treated as 0. So I can see in this bracket minus 2, and minus 2 is less than 1. So according to Macaulay, automatically everything here becomes 0. Same thing happens here. I'm seeing minus 3 here, and minus 3 is less than 1. Therefore, everything here automatically becomes 0. Same thing here, I'm seeing minus 5. Minus 5 is less than 1. So everything here automatically becomes 0. So we have this. So it simply means 0 plus C2 plus 0 plus 0 plus 0. So this actually implies that the second constant of integration C2 is actually equal to 0. So we have that. Next is to substitute the value for C2 into the deflection equation. Since we found C2 now, the deflection equation can now be written as, okay, so the deflection equation can be now becomes, okay, the deflection equation becomes, okay, so we simply have EIY, and that's equal to, we have here 4.05 x cubed, 4.05 x cubed plus C1x. Now, since we know the value of C2, C2 is 0, so it's completely off. Next is to put down your Macaulay's bracket. We have here minus 1.7 x minus 2 to the power of 3. So minus 1.7 into x minus 2 to the power of 3. Okay. We have here minus 0.425 into x minus 3 to the power of 4. Okay. Minus, put down your Macaulay's bracket. Minus 0.425 into x minus 3 to the power of 4. Okay. Finally, put down your Macaulay's bracket. We have here plus 0.425 into x minus 5 to the power of 4. So plus 0.425 into x minus 5 to the power of 4. That becomes the deflection equation. So at this point now, we employ the second boundary condition. What is the second boundary condition? Simply at where? Point E. That will help us now to find the value of C1, or the first constant of integration C1. Okay, so let's do this and see. So applying the second boundary condition, which is at the end of the beam E, so simply at E, x is equal to, now remember we took a section somewhere around here, section xx, and we call distance from point E to the point of section to simply be x. Okay, all right, so now we are simply saying that if x finally extends down to point E, x now will become the total length of the beam, which is simply 2 plus 1 plus 2 plus 1, and that's about 6 meters. So at point E, the value of x becomes total length of the beam. That's simply 6. So at E, x equals 6. But at E also, there is no deflection. Deflection at the very beginning of the beam or the very end of the beam does not exist. Those deflections are simply 0 because we have a point load here. So this point load will counterbalance any form of deflection. So deflection cannot occur at the beginning of the beam, okay, or at the end of the beam due to this point load. So if we had not have this point load here, then it's possible for deflection to occur at that point. All right, so y is equal to 0. There's no deflection there. So we simply substitute these conditions now into the obtained deflection equation. So here now we know the value of y still remains 0. So the equation simply becomes ei in place of y is 0, and that's equal to, next we have 4.05x cubed. Now x has a value and the value is 6. So we simply have 4.05, in place of x, we simply put in 6 cube, okay, plus c1x, in place of x, we put in the value as 6. Okay, put down your Macaulay's bracket. Okay, so we have minus 1.7 into x minus 2 to the power of 3. So that's minus 1.7 into, in place of x there, x is 6. It becomes 6 minus 2 to the power of 3. Okay, put down your second Macaulay's bracket. We have here, um, minus 0.425 into x minus 3. So we simply have minus 0.425 into x, in place of x, sorry, x is 6, it becomes 6 minus 3. 6 minus 3 to the power of 4. Put that your final Macaulay's bracket. You simply have here plus 0.425 into x minus 5. So it becomes plus 0.425 into, in place of x, x is 6, becomes 6 minus 5 to the power of 4. So you have this. Of course, ei times 0, everything here becomes 0. So you simply have 0 equals 6 to the power of 3. That's 216. So you simply have 4.05 into 216. Okay, plus this will give you 6c1. Okay, put down your Macaulay's bracket. This is minus 1.7 into, we have here now 6 minus 2. That will simply give us 4 to the power of 3. Put down your Macaulay's bracket. We have here minus 0.425 minus 0.425 into, you have here now 6 minus 3, and that's simply 3, okay, to the power of 4. Put down your final Macaulay's bracket. You have plus 0.425 into, so we have here 6 minus 5, and that's simply 1 to the power of 4. Okay, okay, so here we have 0 is now equal to, so 4.05 multiplies 216, that gives us 874.8. Okay, plus 6c1, so we have plus 6c1. Okay, now let's consider the Macaulay's bracket now. The values in the bracket are now positive. We have 4 here, you have plus 3 here, you have plus 1 here, not less than 1. So we can now solve with these values. Okay, so simply remove the Macaulay bracket now and solve. We simply have minus 1.7 into 4 to the power of 3. That's 64. Okay, 64. Okay, minus 0.425, 3 to the power of 4. Minus 0.425, 3 to the power of 4. That's 81. Okay. Finally, plus 0.425 times 1. So you can just put that down, plus 0.425 times 1. Okay. So 0 is equal to 874.8 plus 6 C1. Okay, so we have here minus 1.7 multiplied by 64. That's minus 108.8. Okay, here we have minus 0.425 times 81. That gives us minus 34 point approximately 43 plus here 0.425 times 1 remains 0.425. Okay, so we can simply collect like terms. 0 equals, this is 874.8. Let's collect like terms now. Minus 108.8. Okay, bring here minus 34.43. Okay, plus 0.425, and then finally plus 6C1. We simply have this. So 0 equals, so 874.8 minus 108.8 minus 34.43 plus 0.425 gives us approximately 732. Okay, plus 6 C1. So to make C1 subject, we can simply send 732 over here. If positive sign crosses an equal to sign, it becomes negative. So you simply have minus 732 to be equal to 6 C1. And therefore, to make C1 subject now, we simply divide both sides by 6. So this actually implies that C1 is actually 732 all over 6, which implies C1 is equal to, that gives us simply 1, 2, 2. So that gives us a value for the second constant of integration. So all we need to do is simply what? Reflect it into what? The equation. So if we do that now, the deflection equation simply becomes, okay, so we still have this, but now in place of C1, is in place of C1, C1 is now 122. So in place of C1 here, we simply write 1, 2, 2. So it becomes this EIY equals 4.05 x cubed plus 122x Macaulay bracket minus 1.7 into x minus 2, and then the rest. So this becomes the real deflection equation. Okay, so the first question says we should find deflection at point B. The very first question says we should find deflection at point B. Okay, so let's now apply. What to do now is simply what? Apply boundary conditions at point B. Okay, at point B, what is now the value of x? Let's do that now and see. All right, so at point B, that is simply saying x moving from point A down to point B. The value of x simply becomes the length from point A to B, which is 2 meters. So at B, x is actually equal to 2, okay? And deflection at that point is simply called YB, which means deflection at B. So all we need to do is for this value of deflection, we'll simply replace the value for deflection as what? Simply YB, which is deflection at point B, while X is replaced as simply what? 2 meters. So we can find that deflection. So if we do that now, we simply have from the deflection equation, we have EI. This Y simply becomes YB, telling us deflection at point B. Okay, so we have EI y becomes yb equals, so we have here 4.05x cubed, which is simply 4.05. X is now 2, so it becomes 2 to the power of 3 plus. Okay, please take note. I think there was an error somewhere. Please, the constant should have been negative. We have here minus 732. So this is actually minus 732 divided by 6. And that should give us a negative value for the constant. So the constant C1 is actually minus 122. Just an error there. So simply correct this. So we simply have here to be minus 122x for C1 minus 122x. Okay, please just to correct that. All right, so in place of C1x here, which is minus 122x, we simply have minus 122 in place of x is simply 2 meters, so put in the value as 2, put down your first Macaulay's bracket. Here we have minus 1.7, okay, into x minus 2 to the power of 3. That simply gives us minus 1.7 into, in place of x is 2 meters, so you have 2 minus 2 to the power of 3. Second Macaulay's bracket, we have there minus 0.425 into x minus 3. X is 2, becomes 2 minus 3 to the power of 4. Okay, put down your final Macaulay's bracket, you have plus 0.425 into x is 2, so it becomes 2 minus 5 to the power of 4. Okay, so this gives us EI YB to be equal to, of course, this is 4.05. 2 to the power of 3 is simply 8. Okay, simply put that down there, 8. Okay, minus, okay, 122 multiplied by 2 simply gives us 244. Put down your Macaulay's bracket. Here we have minus 1.7 into 2 minus 2 here is 0, so that's off to the power of 3. Okay, put down your Macaulay's bracket. We have here minus 0.425. Okay, into 2 minus 3 here is simply minus 1 to the power of 4. Okay, final Macaulay's bracket. You have here plus 0.425 into 2 minus 5 here is minus 3 to the power of 4. So you have this. All right, so we simply have EIYB is now equal to, so simply evaluate 4.05 times 8. That gives us 32.4. Okay, minus 244. Okay, minus 244. Now let's examine the Macaulay's bracket. We have here minus 1.7 times 0. Of course, everything here is 0. So this is off. Also, we have here minus 0.425 times minus 1. So far, we have negative value in the bracket according to Macaulay's theorem. Okay, when the value in the bracket is less than 1, of course, it is 0. Same thing happens here. We have minus 3 in this bracket, so it's less than 1. Automatically, everything here is 0. So we simply have these two values, okay? So EI YB is now equal to 32.4 minus 244. That gives us minus 211.6. And therefore, you can make deflection at B subject by simply dividing through by what? Flexural rigidity, which is EI. So you simply have minus 211.6 all over EI. And from the question, the values of E and I was given. Okay, so that simply means that deflection at B is simply minus 211.6 all over. The Young modulus is 200 giga, that's by 10 to the power of 9, which is giganewtons per meter squared, multiplied by the moment of inertia was given as 20 by 10 to the power of minus 6. So you simply have this. So this is equal to minus 211.6 all over. Let's obtain these products now. 200 exponential 9 multiplies 20 exponential minus 6. That simply gives us 4 by 10 to the power of 6. So this simply means that deflection at point B is simply equal to minus 211.6 divided by 4 million. So we simply have minus 0.000052 in meters. So this becomes the value of the deflection at point B. And this negative sign simply shows that deflection at that point is simply what? Downwards. That's why we have the negative value. The second question says we should find the maximum deflection. Okay. Now, there are two ways to find the maximum deflection. First is by simply what? Equating the deflection equation to 0. So the whole of this, simply call deflection 0. So equating the whole of this equation to 0 and obtaining the value for x. That point of x is what gives us the value for maximum deflection. But if we look at this equation, we have third power. We also have this to third power. We also have this bracket to to fourth power. So which means it's going to be what? Very tedious for us to follow that approach. So there are two basic methods. The first method is simply by equating this equation to 0 and obtaining the value of x. Whatever value of x you obtain at that point becomes the point of maximum deflection. The second method is by eye gauge. It's called eye gauge. So you simply look at the beam and gauge where the maximum deflection will occur simply by what considering the width of the loads on top of the beam. Okay, you consider the intensity of the loads on top of the beam. So that's the method I'm going to use simply by eye gauge. So we have to weigh the weight on top of the beam and then check where the point that has the higher weight on the beam, that point or very close to that point, that is where deflection is said to be what? Maximum. So I'm going to show you how to do that now so we can all see. Okay. Okay, so to do that, let's simply bring back the original beam. Let's bring back the beam. On this beam, we have the reaction at A. The value is simply 24.3. We also have the reaction at E. Okay, the value is simply 25.7 kilonewtons. Okay, at point D, we have a 10 kilonewtons force here. 10 kilonewtons. Okay, now let's convert the UDL. Remember that UDL was actually between C to D. We are the one that extended this, by Macaulay's theorem so that we can be able to achieve a uniform distance for what the UDL, so that it will be easier for us to integrate. That's why we really extended this UDL down and then counterbalance it on that for equilibrium. So we're still working with the normal UDL. This is point B, this is point A. The UDL is simply between C and D. That's why the UDL is. And the intensity of UDL is simply 20 kilonewtons per meter. Distance between C and D is 2 meters. So I said to convert the UDL to point, to simply multiply 2 by the value of the UDL. So we have 2 times 20, which gave us 40. Then we place it at the middle of the UDL. So here, at the middle of the length covered by the UDL. So we have that 40 kilonewtons load here. So from C to the point load is 1 meters. From the point B to point D is also what? 1 meters. Not forgetting here is 1 meters and here is also 1 meters, while here is 2 meters. So let's now gauge. It's called eye gauging. I have a 10 kilonewtons load here and I have a 40 kilonewtons load here. So it is quite obvious that this 40 kilonewtons load will do more damage on this beam than the 10 kilonewtons load. It's very, very obvious that the 40 kilonewtons load will do more damage than what the 10 kilonewtons load. So which means this deflection will actually what be more around the region of the 40 kilonewtons load. So we simply what if we draw the deflection curve, you see that it goes somewhat in this direction. So it should be more on the side of the 40 kilonewtons load than where the 10 kilonewtons load. So the load should be what? So the beam should be more deflected at the point where we have the 40 kilonewtons load. So we simply find by gauging the value of x. From A to B is 2 meters, from B to C is 1 meters. So from C to the point load where this 40 kilonewtons load is simply 1 meter. So it means that at maximum deflection or maximum deflection will simply occur around where we have the maximum or the greater load on top of the beam. So that simply means that okay, maximum deflection, okay, will simply be at is at x equal, so x is now equal to what? Total length from A down to where? The 40 kilonewtons load, which is 2 plus 1 plus 1, and that's simply 4 meters. So x equals 4 meters. This is where deflection is maximum. So that is the eye gauge. Okay. Okay, so obtain the greater load on top of the beam. The distance towards the greatest load on top of the beam, that is where deflection will be more maximum than any other point or any other load on the beam. Okay, so this 40 kilonewtons load causes more harm than what this 10 kilonewtons load. So deflection should be maximum around the 40 kilonewtons load. So we simply have 2 plus 1, which is 3 plus 1. It takes to get to that point, which is 4 meters. So deflection is maximum at x equals 4. All right. Okay, so we'll analyze my eye gauge and we'll obtain that at x equals 4, y is equal to what? Maximum, y max. So at x equals 4 meters on the beam, that is where deflection is maximum. So we simply put in these values into what? The deflection equation. So once again, EI, we have EI. In place of y there, we simply call that y max, and that's equal to, we have here 4.05x cubed. That's simply 4.05. In place of x is now 4 to the power of 3 minus 244x. In place of x minus 122. In place of x is 4, okay, times 4. Macaulay's brackets, we have minus 1.7 into x minus 2. So in place of x is 4. We simply have 4 minus 2 to the power of 3. Put down your second Macaulay's bracket, minus 0.425 into x minus 3. In place of x is 4. 4 minus 3 to the power of 4. Put down your final Macaulay's bracket plus 0.425 into x minus 5. X is 4. We simply have 4 minus 5 to the power of 4. So EIY max is now equal to, so I'll simply have here 4.05. Let's evaluate 4 to the power of 3. That's 64. Okay, minus 4 times 122 gives us 488. Put down your Macaulay's bracket. This is minus 1.7 into 4 minus 2 here is simply 2 to the power of 3. Put down your Macaulay's bracket. We have minus 0.425 into 4 minus 3 here is 1 to the power of 4. Put down your Macaulay's bracket. We have plus 0.425 into 4 minus 5 here is minus 1 to the power of 4. So we have this. Okay, so we have EI Y max is now equal to, so 4.05 multiplied 64, that gives us 259.2. Okay, minus 488. Put down your Macaulay's bracket. Okay, no need now. Okay, so let's examine the Macaulay's bracket now. I have plus 2 in the bracket, so it's positive. Okay, So which means I can work with this Macaulay's bracket. It's not negative, and the value there is not less than 1. So you can eliminate the bracket. So I simply have minus 1.7 into 2 to the power of 3 is simply 8. Okay. Next, Macaulay's bracket, I have minus 0.425 times 1. 1 here is positive and not negative, so it is simply greater than 1. So I can still work with it. And of course, 1 to the power of 4 still remains 1. So I will simply have minus 0.425. That value multiplies 1 still remains by that same value. And then if we examine this other bracket, we have minus 1 in the bracket. And according to Macaulay's theorem, if you have a negative value, automatically everything there becomes 0. So this man is off. This is completely 0. So I'll just work with that. So we have E I Y max equals, so we'll have here 259.2 minus 488. Okay, so we have 259.2 minus 488. Okay, minus 1.7 times 8. Let's get that value. That gives us 13.6 minus 0.425. Okay, so we have EI Y max to now be equal to 259.2 minus 488 minus 13.6 minus 0.4425. That gives us minus 242.825. Okay, therefore to find the maximum deflection, we simply divide by flexural rigidity. This simply implies that Y mass is now equal to minus 242.825 all over flexural rigidity, which is E. And of course, we know the values of Young's modulus, we know the values of moment of inertia. So this simply means Y mass is equal to minus 242.825 all over Young's modulus is 200 giganewtons by 10 to the power of 9 multiplied by moment of inertia gives us 20 by 10 to the power of minus 6. And this is equal to minus 242.825 all over 4 by 10 to the power of 6. Okay, I think I can take this off. Therefore, Y mass is equal to minus 242 divide 4 exponential 6. That's minus 0.0000607 in meters. So this becomes the value for the maximum deflection. And once again, that value is negative because deflection is tilting downwards. Okay, so that gives us the value for the maximum deflection. All right, guys, so I hope you find this video very interesting and helpful. Please, if you do, I would like to get your thoughts in the comment section. I would like to get your thoughts in the comment section. All right, so if you're new to the channel, please don't forget to hit the subscribe button and, of course, share this channel continuously to your colleagues and your classmates, who are also finding difficult to work engineering problems which you are dealing with in this channel. All right, I will see you in the next video with more and more amazing question on beam deflection. Thanks, guys, and cheers.